damped simple harmonic motion. Damped simple harmonic motion. When the motion of an oscillation is reduced by an external force, the oscillator and its motion are said to be damped. In this case, without the bottom part, this is called simple harmonic motion. But we connect this map with an organism put in the water, so it will have a resistance proportional to the velocity. The FV called minus BV. In this case, we put in sign. So sigma F equal to Hooke's law and resistance velocity. What is this one? This is equal to dV dt. This one, sigma F equal to MA. Right? Yeah. This is equal to MA. This is equal to minus K. V is dx dtB. Okay. Or this equation, we rewrite it. Okay. M dx dt, move this here. B dx dt plus x dp. This is a second order differential equation. Okay. Linear, because it's all linear. And we want to find the answer of this one. We know that once you have this term, IBT, the vibration amplitude gets smaller and smaller. So we assume beside the xm cosine t, you have another term, e minus at. As time goes up, this one goes down. So it gets smaller and smaller, okay, reduced, okay. So we assume the answer is this one, and we put this one here. We can do the derivative, okay. So you have two terms. The first term is minus a plus e cosine, okay. And second term is cosine is minus sine, and had omega. Okay, so we had a blue one, 1, 2, 3. First one is the red one. So we have two terms. What is this one? And we see the second derivative. So we do this and do this. Do this is minus a again. Minus be the xma squared. Okay, and the second is you cosine. Cosine is minus sine, minus positive. It's xm a minus a is omega. It takes the omega sign. And this one you have minus a minus, you get a positive xm a omega. Okay, and got a second you have cosine. It's minus cosine omega. It's omega squared, omega. So we get this too. Now let's multiply k on the side because you have kx. And then we multiply b on this side. You have b multiplier of this one. And second derivative, you have m. You get an m. And then we put them together. Now, here you get an mx second derivative plus b dx. This is equal to 0. And here we see a lot of sine and cosine. And we combine all the cosine term and all the sine term. We see the cosine term. This one, you had a kxm. This one is minus bxma. Okay. This one, you have positive mxma squared. And this term, minus x omega squared mx squared. This one. Sine, this is sine. You have b minus b xm omega. Minus b xm omega is the sign. Another sign is, see, m xm a omega. M xm a omega is 2 ma x omega. So this one. Now look at this equation. This equation should be equal at any time. What the result? The result is only possible if the coefficient equal to 0. Okay? All that, we make this equal to 0. Okay, you cancel the omega xm, so you get the a equal to, get a b equal to minus b, a equal to b over 2m. Now, we get this one. Relative b and m. You put am inside, we get omega. Omega equal to k of m, b of m squared. And k over b is omega 0 squared. So originally, usually this term is much smaller than this term. We drop it. Get the frequency. It does not change too much. Okay. All right. We have a, then we get an answer. We get omega. So x equal to xm, e to the minus b over 2m. Okay. Cosine omega. This omega is this omega plus 5. Okay. Then the oscillation. This is the one. Beside the vibration cosine, we have external, extra, potential okay, term is minus. So as time increases to 0, this term decreases to 0. Okay, equal to 0. All right, and then we have omega equal to this one. Okay, now we look at when the vibration, this one we call terms amplitude. Amplitude gets smaller and smaller, smaller and smaller as time goes by. Okay. Now we see the energy. The energy could have mxm squared, and at time t, because this term changes, so this becomes xm plus this is square to e minus bt over m. So the energy get less and less where it is consumed by friction. Okay. The mechanical energy decreases exponentially with time. Sample. For the damped oscillator of the figure, M 250 gram, K 85 Newton per second, and B is 70 gram per second. What is the period of the motion? We just put it in the formula. Okay. Km is 0.25 kilogram. B is 70. Okay. This is we should use the kilogram. So it's a 0.07 square. Okay. Yeah. And this one we find out B is much smaller than KB. So this term can be dropped. We get this one. Okay. So omega equal to omega 0. Okay. And the T is the same thing. Very easy to find out. Okay. How long does it take for the amplitude of the damped oscillator to drop to have its initial value? Initial value is this one. Now we got half. What is half? Half this one. Okay. Now there's half this one. When t equal to 0 is xm. How long? You got to half, and we take so. We cancel the xm. We do the log. So, okay, this is equal to log this equal to log half. Okay, log 2 half. This side we get minus bt over m. Okay, and this side we get minus log 2. They are equal. Okay, then you find this one. The t, okay, is log 2, 2m log 2 over b. We find the answer. Question C. How long does it take for the mechanical energy to drop to 1/2 its initial value? This is amplitude drop to half. This is energy drop to half. Then we see what the energy? Energy could have m xm squared times t, and you have this t. Okay, this is equal to half 0, E0. E0, this is equal to 1. So equal to half E0, half fmkxm. Then we see cancel the half k, cancel xm, we do the log, we can find the t. Okay, similar to this one. That's it. That's it, only 2.5 seconds faster than the amplitude deteriorate.